Hi, welcome back. So in the previous videos, we've just had a look at defining what the Astar algorithm is, its search strategy. We've talked about essentially some of the properties of the Astar algorithm. It's complete and optimal. It's really great in practical performance, and it has this idea of it being optimally efficient, right? So that main video is the one that this follows on from. Hey, if we just proved essentially that the Astar algorithm is optimally efficient, no other algorithm that is less informed could possibly expand fewer nodes, right? That's the statement we've been making. Well, then it becomes a little confusing, right? I think the follow-on question is, how can we even improve the Astar algorithm then? Well, the Astar algorithm has been around since 1968, and I will give you the spoiler in that there has been a substantial amount of work on state-of-the-art in the area of heuristic search and otherwise, all improving upon the Astar algorithm. What is kind of fun though is that a lot of these really do build directly on top of it. We're improving the Astar algorithm through modifications and actually tackling other areas, other aspects of the problem itself. So in this video, I want to discuss how we're going to improve the Astar algorithm. Over here, I'm going to write down a list. There are going to be 4 main ways we're going to talk about in terms of improving Astar. So the first of which is we can improve essentially the direct translation of our original problem, often a real-world problem, right? Or sometimes it's already a fake problem. It's like a video game map or something like this. But we have some way of translating the state space, the original problem space, to the search space, right? To the version of the problem we're going to be solving. Now, what's happening here is that there is a level of abstraction, okay? So oftentimes we're removing a lot of the important or perhaps not necessary aspects of the state space and of the problem in order to be able to efficiently and happily solve problems, which we can then map back from the solution to the original problem, to like a sequence of actions that our robot or ourselves can actually perform in order to solve the problem. So that abstraction can be extremely important in improving the practical performance and speed of our algorithms. So in the case that we had states not only being, say position, imagine you also have direction included in your state. So you have a robot whizzing around in a maze, and it has a current direction that it's pointing, right? You're trying to escape the maze, you're trying to plan a path to get out. Well, in the state space, in your search space then, you're going to be searching over, you could reach the same state pointing in 2 different directions, right? Each of those would be separate search nodes. They would have obviously a much larger branching factor. The problem would be a lot harder to solve. Well, we can do clever tricks, right? We can reason over the problem environments itself, rephrase the way we think about it in order to massively improve our search algorithms. So a very, very simple and a very common one is that we can simply abstract away search direction. If we're happy with its grid distance that we're optimizing, right? Well, we can have direction as an implicit part of the state. If we search only on the XY locations, you will eventually, we can build in to the expansion of a node, to when we generate children, we can only generate children that are valid based on the direction we came from, right? So all of this can be implicit calculations within our expand function that is a separate idea than it existing in the search space itself. This means that our algorithms can actually be substantially faster. So that one is a long-winded answer, but simply we can reduce the search space via abstraction. Abstraction. Okay, so by reasoning over the world, we can simplify our problems, which simplify search, and ta-da, we get massive improvements. So that one I think is a little bit separate, right? Because that's almost like the precursor step to us solving the problem. So the other 3 then are going to be, we are now given the problem, we're running our search algorithm, what can we do to improve it? The first one then is, let's dive into the idea of implementation, right? So we have implemented the Astar algorithm. You had your concepts of things like tree search versus graph search. Graph search is going to be much more performance, right? It has a smaller tree, things like this. But essentially, how about such data structures as the open list and the closed list? During search, we are going to be querying node expansions, node generations, which involves a whole series of inserts and deletes and relaxations of nodes in some form of queue, some form of priority queue. And so the way that we implement that in our code has a substantial impact on the speed of our algorithms. So we'll see essentially that the Astar algorithm is very, very often implemented as a heap queue, just as a binary heap. And this makes it very easy and efficient to have these we'll call them log n, these very quick operations for the inserts and the pops and the relaxations that happen constantly throughout search. And those are happening every time for every node that we're generating and so forth. So these are very, very popular steps. And what I'm trying to say is that the way we implement data structures has obviously an important impact on our performance, and you can improve the Astar algorithm by implementing better data structures. As a small note to that as well, on top of just using like a binary heap, there are, if you're familiar with some really advanced data structures and algorithms, in computer science there's this mythical being that is the Fibonacci heap, right? Which promises these substantial improvements, actually, beyond your standard algorithms in its worst case time and space complexity. So hey, maybe we could implement a Fibonacci heap in the open and closed list. But I think the idea is the Fibonacci heap is extremely complicated to understand and to implement. And so on top of that, in terms of practical performance, it doesn't seem to really offer substantial or significant improvements over the simpler version of these implementations. And so I think more often than not, we do not opt to choose these complicated beasts when we can have a similarly functioning but much easier to understand and implement data structure. So that's something I just wanted to note. Okay, so next, well, we've already talked about improving the initial stage, translating the problem into the search space that we're going to search over, right? Then we've talked about, okay, well, how about implementing the code? Can we make substantial improvements there? The next step then is, hey, can we improve the expansion, the search progress itself? Well, we have that the Astar algorithm is, of course, we've seen it's optimally efficient in terms of node expansions. That means for the same heuristic, we can't improve, we can't expand fewer nodes outside of tie breaking. Now, okay, well that then leads, I think naturally then, we can't improve G, the cost so far. That's just literally in the problem itself. What was the cost of the actions I've taken? But we can look to improve the heuristics themselves. So I'll write that down. So we can improve by creating better, more informed, more accurate heuristics. So by reasoning over a very specific problem domain, maybe we can come up with, as human beings, some nice way to quantify, hey, how far away do we think we are, right? And so if you can come up with something that is still both admissible and consistent, but actually is oftentimes or is sometimes more informed, right? It has a better estimate of really how far we need to go. Well, then we can kind of pair this with our other heuristics. And if you remember, when you use heuristics, you can kind of actually try a whole bunch of them as long as they're fast to compute. That can kind of still mix and match, and you can always pick the best one based on whether it's more informed, as long as they're all satisfying admissibility and consistency. But yeah, so a lot of the work in state-of-the-art algorithms as well is coming up with improved heuristics, or perhaps improved ways of dealing with the memory consumption of perfect heuristics, mixing and matching between, we don't store all of the heuristics, but maybe we store some of them and abuse that information. So there's a whole lot of really fun and interesting ways to improve heuristics. And of course, that means that we'll be able to expand fewer nodes during search because our F values will better reflect the true distance to the goals. And that means, of course, we are improving the A-star algorithm itself. And so finally, I think this is the one then that maybe is a little harder to see initially, but it is the most, I think, well, I would argue the most important, maybe alongside with the heuristics aspect, the most common way in the literature for us as researchers and as students to improve the A-star algorithm is via reasoning over the problem and pruning parts of the search tree, right? We can reduce the search space by doing additional reasoning so that we can eliminate options we know won't be necessary. The issue with search, of course, is that the search tree grows massively, and by leveraging human intuition, we can oftentimes find really clever tricks in order to. It's somewhat similar to abstracting the initial problem, but right, we're in building this additional level of abstraction or directly reasoning over the world, over the grid, to maybe we come up with compartments. Hey, here are a bunch of rooms. I can treat these as separate components, things like this. Maybe we could draw bounding boxes around search. Well, we know we never have to go outside of this box, things like this. We can do extra work up front or in an online setting to improve the overall performance of the search itself. So that's really exciting. So I'll write that down here. So to write that down, we're often, right, when we're doing this reasoning to prune things, it's almost like we're imposing constraints on the valid generation of children, right? So it's often then just called constraint-based pruning. Now, obviously the terminology pruning here is aptly coming again from the idea of a search tree. We are culling, we're pruning off some of those branches, right? We're saying, hey, this branch we've kind of realized won't be necessary. I can cull it, I can prune it from the search space. Makes sense. So to give you some brief examples of the terminology, the different types of ways that we can prune things, oftentimes this is either in terms of feasibility. Okay, so we should be able to prove that some of these nodes that we're kind of generating and would otherwise be tracking in the search tree, well, they're not either required for feasibility, or they could even sometimes not actually correspond to feasible solutions. We just haven't yet discovered that. So I would call these ones feasibility-based pruning techniques. And then there's other ones. I think one of the main common ones is symmetry-based pruning. So if you think about it, a lot of the search tree, if we went north then east or east then north, well, we're obviously getting to the same location, right? Through different versions, different symmetrically equivalent paths. So we can do a lot of reasoning over that. Our algorithms, our computers are not smart enough to recognize that these permutations perhaps correspond to similar versions of the solution or of a path so far. And so again, we can kind of reason over these worlds and prune things based on it being a symmetric equivalent to some other node. So I'll write these things here. So we just have the idea of some of the constraint-based pruning approaches is feasibility-based pruning and symmetry breaking or symmetry-based pruning. Okay, so ta-da, we absolutely can and we absolutely will improve the A-star algorithm. A lot of this is actually just to say that this is actually quite exciting for at least us as humans and particularly us as researchers. So despite the fact, right, that we've seen that the A-star algorithm is the optimal, it's the best search strategy. We can't really improve upon the order we expand nodes. What ends up happening then, the ways we have to improve our algorithms is through this additional, essentially, reasoning over problem-specific knowledge, over domain knowledge, over ways of representing problems, over ways of implementing our algorithms, over ways of defining heuristics. So all of this, right, is, if you think about it, this is good for us as humans. It's fun. It means that a lot of the improvements, the knowledge gains we can make in these areas, the ways we achieve state-of-the-art, is with human reasoning, applying human intuition, human problem solving, human pattern recognition to solve and improve our algorithms. I think this is quite exciting, right? Especially in the context of the rise of, I think, other AI like neural networks and LLMs and things like this, right? Where there are these black box models. We as humans are not really, obviously there's a lot of innovation in terms of the architectures and things like this, but I think I'm free to say that the actual way that these are learning is still absolutely hidden. It's within this black box, and it's nowhere near as driven, I think, by human creativity, human reasoning. And so I think what's really a really powerful and exciting aspect of pathfinding and heuristic search, right? These, not only are these problems so visually appealing, so visually accessible, you can see the search tree, you can see the initial problem, you can see search progress, and I think it has that beauty to it as well. But yeah, I especially in the last 4 years of my PhD, I can prove, I think it's just also fun to reason about, fun to problem solve, fun to try to come up with creative ways to go, well, actually, maybe if we thought about it this way instead, can we abuse the fact that, like, hey, sometimes it's easier to search from this way instead of that way? Is that information I can use and change the way I view the problem and solve the problem? Is that even important, right? And then you do your little deep dives, you discover new things about the world, algorithms, how things interact. And so yeah, I think all of this is really important. And let's then talk about essentially where we're going to move forward. Please stay tuned for our deep dives into state-of-the-art. I think in terms of this series here, Pathfinding Fundamentals, I'm going to be continuing onwards with, there's much remaining, right, in terms of hidden complexity in how we attempt to solve problems when aspects of the problem change, right? Maybe obstacles move. Maybe there's time, right? We haven't even dealt with time yet. Maybe our agents have size, right? And they'll hit walls and things. Maybe we don't care about getting the optimal solution. We just want something close. So there's a whole realm of possibilities. Oh, and then of course, actually, we're really going to move towards as well multi-agent pathfinding, which is its own, we call it it's an entire own field, multi-agent pathfinding, MapF. So there's a whole ecosystem of algorithms that we still haven't explored. What's really exciting is so many of them build upon these basics here we've defined in terms of the Astar algorithm. So be excited for those videos to come soon. But I'm also going to make another series essentially on state-of-the-art pathfinding, including MapF algorithms, where I go into a deep dive onto the ways that we are really achieving cutting-edge technologies in search. These are used in real-world applications, from video games to robotics, and I think they're really, really underrepresented here on not only YouTube, but just in the wider world outside of these university classes or hidden away behind the doors of Amazon or so forth. So I'm really excited to share a lot of that with you, and please join me for those videos and the next in this current series. So thanks, and see you soon.